So good afternoon, everyone. Apologies for the video lecture. Family got really sick and I am still recovering. So I apologize, we're going to have to miss the in-person lecture tomorrow. So a couple quick announcements. Apologies again, we will not be doing the office hours on Monday. As I mentioned, I'm going to be sick. There will be the TA tutorial tomorrow on the Tuesday. One quick reminder, as I've mentioned before, midterm 1 is coming up, so please make your bookings with the CFA if you are registered. One other part I want to bring up though is this portion here. So every year I invite students to create a midterm style question and post these on Piazza. The rules of it is to create a question that you would like to see, something that sort of tests the material that we're going through. Post it on Piazza, including a answer for your question. Now, this can be anything. Now, I really encourage you guys to engage in this for two reasons. First, it's a good practice for you to start creating a kind of question that is relevant to the material we're covering. It helps you to test your own understanding of it. And in fact, what I will do is actually take one of the questions that gets posted and use it on the midterm. In other words, it's a way for you guys to structure a question, practice it amongst the class, and I will create a question based on that one that will be included. So you guys will have a bit of practice ahead of time for one of these kinds of components. Now, last class we talked about oxidation reduction reactions. We brought up this concept of a reductive amination, and then we gave you two new reactions that were resetting or removing a carbonyl entirely. The Wolff-Kishner, which it's special because it happens under strongly basic conditions, and the Clemmensen reduction, which happens under strongly acidic conditions. So those are used in cases where you're doing sort of modifications of a molecule. The reason we have acidic and basic is sometimes there's other functional groups which are not compatible with those conditions. So we have to choose something that would allow us to do usually targeted or surgical reactions. So for the review question for today, first thing to start off is to predict the products of these two reactions. This is a review from previous Chem 203 or 233. Take a moment and think about what answer you might come up with. Okay, so if you go through this, we're using Jones conditions in both cases. The main difference between the two, this is a primary alcohol, this is a secondary alcohol. And as a result of that, the oxidation that we're going to incur on the top one will go up to the carboxylic acid. Bottom one will stop only at the ketone. So this is a change in oxidation state of 1. We go from an alcohol to carboxylic acid, so it's a indexing by 1 level. Alcohol up to the carboxylic acid, first down here, the ketone, is a change in oxidation state of 1. Here to the carboxylic acid, this is 2. It'll go up first to the aldehyde, and then the aldehyde then continues and is oxidized further. Now, look at this one. What do you think the product of this particular reaction is? So this draws back to the conditions we discussed last time. All right, if you remember, this is the Wolff-Kishner reaction. So what we're doing here is we have hydrazine and heat, and we have a carbonyl. That is going to give us an intermediate under the first step to CF3, and it will create the hydrazone. The hydrazone is the condensation product. It's similar to the imine reactions that we've discussed before. And this is our C phenyl 3. Remember this designation, this phi, is actually shorthand for a phenyl group. So phi is equivalent to pH, so it's just a shorthand of 3 phenyl groups. So that's the first intermediate we generate, treating that under strong basic conditions, ethylene glycol and heat. That's going to allow us to carry out the rest of the Wolff-Kishner. And as a result of that, we will have our deletion or removal of that carbonyl group. So the rest of the molecule should stay intact. The imidazole, the C, phenyl 3, and methyl is all still present. This center that used to have the carbonyl will now just be our methylene. Okay, so today we're going to be moving over to talk about carboxylic acids. This is chapter 19 in Voldhart. If you're using the older Brown textbook, it's chapter 17. We're going to talk about carboxylic acids and their properties, how we make them, the possible synthetic routes to these molecules, and then what we're going to do is our primary routes to generate them from oxidation reduction reactions and nitrile hydrolysis. So first off, if we generally talk about carboxylic acids, you guys should recognize this from previous. The carboxylic acid functional group contains a carbonyl. We now have this higher oxidation state where we have this OH attaching to that center. So the entire piece, this center here, this COOH, is what makes up the carboxylic acid functional group. The main thing about it from naming, you guys remember, has this oic naming. So common name would be something like formic acid or acetic acid. But we can also, when we go to longer chains, you see butanoic acid. That OIC is what we use with our normal IUPAC naming, where we're bringing in things like the carbon bond length. So prop is our 3, but is our 4, and this oic acid is our the naming convention. Now, in general, there are a lot of common names we use. So, for example, benzoic acid is talking about the benzyl functional group. It's the aromatic ring plus 1 carbon is what we're determining for that component. Formic and acetic, these are just very common names for short carbon groups that we've used, and you'll see these appear in reagents. Just to name some other ones that come up, these are good ones to have knowledge of. These are not specifically things that we may test in terms of their names and structures. What I'm expecting for you guys to know is that if you see a name like acrylic acid, oxalic acid, succinic acid, you know what that we're talking about carboxylic acids. These are common carboxylic acids that we're going to be referring back again. In particular, malonic acid is one that we're going to be discussing quite a bit later because it actually makes up a carbon fragment. It's a 3 carbon fragment that we use for specific kinds of synthesis. So again, the ask right now is recognize the names, be familiar with what they are. Generally, we will also provide you with the structure, so we're not going to be doing something like draw the structure of succinic acid versus glutaric acid. But if we do refer to something like it is a reaction with succinic acid, it might be useful to remember that these are dicarboxylic acids in particular. As you notice, almost all of these ones over here are common groups that actually contain 2 carboxylic acids built into them in the molecule. Acrylic acid is one that we may discuss a little bit more. What happens specifically is it contains this alpha-beta unsaturated unit. So that's where we have a carboxylic acid with this double bond adjacent to it. So as far as physical properties, carboxylic acids are unique just because they are going to be on the acidic scale in terms of the pKa. If you remember, generally, carboxylic acids are going to have a pKa in the range of about 4 to 5. Now remember, the pKa equation shown here is how protonation happens, where we're using transfer of a proton to water. This is the Ka equilibrium expression. Part of the reason that they are so acidic comes down to this resonance stabilization. So the negative charge that's generated after deprotonation here is resonance stabilized all the way through the oxygen center. So this is similar to what we've seen with things like enolates. The alpha protons on the carbon that is alpha, so at this position just adjacent to the carbonyl, is more acidic because a negative charge in that position alpha 2 carbonyl can undergo resonance stabilization, which allows it to be a more stabilized conjugate base. As a result of that, this is far more acidic than a typical alcohol would be. Again, you've seen this in previous years, and we're just giving you a reminder of that component now. So the thing to remember about this is that in general, anything that affects the relative acidity of this acid-base equilibrium is easy to manipulate just because of the same properties that we've seen that give you stabilization of our anion. In other words, if I have a simple carboxylic acid like this acetic acid, we know that it's relatively acidic. This anion is relatively stabilized because of that resonance effect. But it also means if we were to add things like other electron withdrawing groups at this center, we're going to generally acidify this carboxylic acid even more. So while something like the acetic acid is going to have a pKa in the range of about 4 to 5, adding something like fluorines to the center will generally drop the pKa down, making the carboxylic acid subsequently more acidic. The same rules that we've talked about in first and second year about modifying or ranking the relative acidity is what we're really going to be touching on. Again, what we're really discussing here is that anything that we do that helps to stabilize the conjugate base that you have to form here will generally push the equilibrium in favor of that conjugate base, making this carboxylic acid more acidic as a result. So just as a reminder, carboxylic acids generally fall in the category of a weak acid. And remember, what we're really just trying to come back to is that even though the pKa of most of these carboxylic acids is in that range of sort of 4 to 5, there's sort of two parts that we want to point out here. The pKa is a fundamental property which ranks the overall acidity of some species. It tells us where or how acidic one carboxylic acid is relative to another one. So it's the a property, a colligative property of a molecule that talks about overall how badly that acid wants to dump a proton. The pH is a specific measurement of how many or what the concentration of H3O plus is in solution. So think of it where you can have a solution of a acetic acid. So while acetic acid may have a pKa of 4.76, you can have a number of different solutions of acetic acid with different pHs. So again, acetic acid has a fundamental value. It has a pKa of 4.76. That's like saying its boiling point or its density. It's a colligative property of the molecule itself. However, depending on the concentration of acetic acid or how much other base is present in solution, we may have different ratios of both the conjugate acid and the conjugate base in that equilibrium. That's defined by the Henderson-Hasselbalch equation. So the pKa is that sort of 50-50 point, halfway in between, where we have equal concentrations of both the acid and base form of our weak acid. And then if we go plus or minus 1 pH unit, we can get that sort of 10-to-1 ratio in favor of the acid, or on the other side, we get this 1-to-10 ratio in favor of the conjugate base. This is what we usually defined as the buffering region. So it's from our pKa, it's that range of plus or minus 1 pH unit. And during that region, the solution will typically resist a pH change. And again, that's all been defined as we used to do calculations with the Henderson-Hasselbalch equation. The thing we're just really calling in is there's two parts. As you change the structure of a carboxylic acid, the pKa may shift, where if it is less acidic, the pKa generally goes up higher. If the molecule is generally more acidic on average, the pKa will drop down. And for every molecule with a fundamental pKa, it could exist within a certain range of solution pH, depending on the other components of the system. So just as a quick example, like we brought up before, generally electron withdrawing groups will tend to increase the acidity, dropping the pKa, and electron donating groups will do the opposite. It'll tend to decrease the acidity or increase the pKa. So if we look at this series, you should be able to rationalize the changes that we're observing here. So taking 4.76 as our reference point where we have just hydrogens here, notice if we donate these methyl groups on here, these methyl groups generally can be thought of as electron donating groups. They have alpha protons around here that via hyperconjugation tend to be increasing the electron density towards the center. So as a result of that, the more alkyl groups you add to it, you get a slight destabilizing effect, and the pKa goes up just slightly. And again, it's not much, but generally it becomes less acidic as you add these other carbon groups attached to it. These ones should be obvious. As you add chlorines to that center, these electron-negative groups, what you're getting is induction, which is pulling charge density along the sigma bond skeleton. So having a single chlorine on there will actually do quite a bit in terms of the increased acidity. Adding 3 chlorines altogether has a much, much larger impact, dropping the pKa down almost to 0 in that sort of case. If you remember in previous lectures, we also discussed TFA, or trifluoroacetic acid. That's this molecule. Again, this is even more acidic because you have a much more electronegative fluorine relative to the chlorine in that case. Now notice that going to something like this aromatic group, there's not that much of a change in the overall acidity. So yes, having this aromatic group here will tend to stabilize the anion. The most important thing is that there is actually no resonance possible in this system. So what I mean is no resonance. There's still resonance here, right? That resonance stabilization is possible for the anion, but if you go through and draw the different possible structures, what you'll notice is that the anion that you would generate that is in resonance over here does not cross-conjugate or otherwise delocalize to this ring itself. So you're getting only a mild stabilization, mainly because of sort of the relative electron withdrawing character almost of the aromatic ring, the sp2 center adjacent, but you're not getting this drastic stabilization that's possible because the anion that you might generate at that carboxylic acid center is not easily delocalized into this aromatic ring to any significant effect. And again, if you draw out your resonance structures, you should be able to prove that to yourself as well. So if we're going to actually form these, what we have to do now is connect them to the fundamental reactions that we've described before, how we might generate them and how we might carry these through to other different fragments. The main ones that you guys should be, in terms of their formation ones, oxidation reactions are probably the most common ones that you've seen. These are things like the Jones reaction and different chromium reactions where they're coming from either an aldehyde or an alcohol, something from the lower oxidation state. As far as what we do with them on the same kind of level, reductions are possible. This is where we could strip them back to things like our alcohols in that part too. So think of this as, at least within our oxidation reduction points, we form them from the lower oxidation species like alcohols, and we can return them to those alcohols by a reduction type reaction. Option number 2 is what we call nitrile hydrolysis. So this is where we're switching a carbon-nitrogen bond into our carboxylic acid. So this is where we're stripping out the nitrogen or as ammonia, where this carbon center here is that carbon center seen here. Now if you notice, they look very different, but they're actually at the same oxidation level. we have 3 carbon heteroatom bonds, and once again 3 carbon heteroatom bonds here. It's just that in this case all of them are bonded to the same heteroatom. Here they're split 2 and 1, but overall still same general oxidation content. Approach 3 would be our organolithium, or our capture of CO2. So this is where what we're doing is we're starting from a Grignard reagent, and we're actually attaching a new carbon to it from CO2. This would almost be like a small reduction reaction. We can actually do the opposite, where we do what's called a decarboxylation, where we eject or lose CO2. When we do this, part, we can actually eject CO2 from the reaction to regenerate something like one of our precursors. Our final one we're going to discuss is called a haloform reaction. This is where we're using the bromination of a ketone type compound, and we're fracturing the carbon-carbon bond. So I'm just providing these as some guideposts for the kinds of reactions that we're going to be discussing through, mainly focusing on number 1 and number 2 in today's class. So the first, if we're going to be generating carboxylic acids, if we're doing it from these ones, we're going to oxidize a primary alcohol or an aldehyde. There've got to be cases where there are at least 1 or 2 hydrogens on the carbon, which we are taking up to this, this higher oxidation state. So this carbon center here is the same atom that we're turning into these higher oxidation components. So the focus here is that these oxidation reactions are just reformatting this carbon center. We're not adding a new carbon to the chain. We're not doing anything else that's fundamentally changing the carbon skeleton. We're just reformatting this functional group into our higher oxidation ones. And again, you've seen these from previous years primarily. On the other side, just to keep it consistent, once we're at this higher oxidation state, this carboxylic acid, we can actually return it to the alcohol, but that's going to require us to use a reduction, and more importantly, to take carboxylic acids all the way back to the alcohol. We're going to do this with lithium aluminum hydride. It's the super powerful hydride reagent, much more powerful than sodium borohydride. So it's unique. This is the only reducing agent that we have available to do this. And these hydrogens here are the ones that are being inserted into that center. So those hydrogens act as our nucleophilic hydrogen source, reducing that center and then coming back. But once again, we're not changing the carbon bonding skeleton. This carbon here is the same carbon we have there. We're just changing the heteroatoms attached to that carbon as we reformat it. Just as one quick note, the reduction of carboxylic acids really focuses on this lithium aluminum hydride reagent, and we're going to go 2 levels. So here, if you think of the carboxylic acid at sort of the oxidation state 3, that's where we've got 2 and 1, we're actually dropping down to oxidation state of 1. So there's actually 2 different reductions that have to happen as we move through this one. That's reflected by the addition of these 2 hydrogens as we go through here. So we're replacing this complete carbon-oxygen double bond. Both of those are being removed to get down to this level here. We'll talk about the mechanism of that in a bit more detail in the coming classes, but for now this is really just a guidepost for you guys. One thing to mention, catalytic hydrogenation is not effective on these molecules. It will reduce things like aldehydes, ketones, alkenes, and alkynes, but it is completely useless for trying to reduce carboxylic acids, and we'll discuss that a bit more a little bit later on. The other thing to mention too is the other hydride reducing agents that we've talked about, sodium borohydride or even sodium cyanoborohydride. Once again, these are not powerful enough to reduce carboxylic acids either, so you're really stuck with this single reagent as our major one. On the other side, something to remember is that alkenes, our carbon double bond reagents, will not reduce when we have things like even lithium aluminum hydride. So metal hydrides are exclusively for reducing carbonyls. Hydrogen over palladium kind of can do a little bit of both. It can do both the alkenes as well as the sort of lower oxidation state carbon double bond oxygens. And that's where this combination of different reagents having different specificity can be used to in synthesis with different kinds of selectivities that we're hoping to achieve. So take a second here. If we presented you with a molecule with multiple different kinds of functional group, based on the reducing agent that we're applying, we should be able to surgically go through and choose which functional groups get attacked. So take a second. I'm going to pause for a second and ask you to think about what your answers might be. We can do the explanation now. Okay, so let's take it moving from, first of all, hydrogen over palladium or platinum. So these type of reagents, remember, are primarily designed for carbon-carbon bond reduction. So the alkene is the first one you should be targeting here. We mentioned last time that aldehydes and ketones are also in scope. However, centers like these carboxylic acids will not be affected. So if I did this reduction, I would expect that the carboxylic acid is going to remain, to be untouched from these conditions. The other centers that are being attacked, the carbon, double bonded carbon, is going to be reduced to a simple alkane, so we just have only hydrogens there. And up top, the alcohol would be remaining up there too. Just as a quick bit of note, in general, hydrogen over platinum are these metal hydrogen type conditions, since they are most selective for things like our carbon double bond. Carbon centers, alkenes and alkynes, those will typically reduce faster, where only after time you'll start to nail these aldehydes or ketones. It's just generally the reaction is much more selective for our carbon-carbon bonds, but with enough hydrogen and time, you will hit both of them to give you something like this. Okay, in the next one, let's do the sodium borohydride. So this is a hydride reducing agent. It will not touch carbon double bonded carbon, but it will attack carbonyls. So the alcohol will be reduced, or the ketone will be reduced to the alcohol. The carbon double bonded carbon, the alkene, will remain intact, as well as the carboxylic acid. That's not going to be affected by these conditions because even though it's a metal hydride, it's not powerful enough to reduce the carboxylic acid. So we're stuck here. In the last example, lithium aluminum hydride, once again, this is a hydride reducing agent, a metal hydride reducing agent. So it's not going to impact the alkene. This is designed to take out the carboxylic acid, but it takes out any other carbonyl as well. So in this case, the ketone will be reduced to the alcohol. So you'd end up with this diol sort of system. Okay, so now we're going to discuss approach number 2. This is how we would form by hydrolysis. So in this case, we take a nitrile. Remember, a nitrile is a carbon triple bonded nitrogen, just like this, and under both acidic or basic conditions, what we're doing is we're using water to split this carbon-nitrogen bond and replace it with only carbon-oxygen bonds. As I mentioned before, look at the oxidation state. So this carbon here is this carbon here, and what we have here is 3 carbon to nitrogen bonds. So you can think of it as a third level oxidation. Here we have 2 carbon oxygen bonds plus 1 carbon oxygen bond, total of 3 carbon oxygen bonds. So even though we're switching a nitrogen to an oxygen at each of these centers, they have the same oxidation state. In other words, we're not doing a redox reaction. We're not changing the oxidation state of it. We're just shuffling around the bonds that are present. So it's a rearrangement more than it's a change in oxidation state. Once again, that carbon is this carbon centered here. So we're also not changing the carbon skeleton. We're just hydrolyzing the carbon-nitrogen bonds, swapping out these carbon-nitrogen pi bonds for things like carbon-oxygen sigma and pi bonds when we're done. So nitrile hydrolysis, under both conditions, acidic and basic. We're going to talk about the mechanism in the coming systems, but they follow very much the same kind of logic that you've seen for imine chemistry. What we have here is a relatively stable system. This carbon-nitrogen triple bond here is pretty stabilized. In order for water to act as a nucleophile, what we're going to do here is first activate this nitrogen, probably by protonation. Once we've done that, we're polarizing this bond, making it more susceptible for nucleophilic attack. So we're increasing the general electrophilicity of the system by first ramping up the overall polarization of this bond. That allows the oxygen to act as a nucleophile, which then is going to undergo this transformation you see here. So let's walk through this. Again, the philosophy is what I sort of described through. We're going to start by first activating the system, giving us now this more electrophilic carbon-nitrogen bond, where we've now protonated that center, and we now have our, let's say, the water as our potential nucleophile. Now that we've got this oxygen nucleophile, we're going to attack the electrophilic carbon, similar as we have with the carbonyl-containing molecules we described in the first couple lectures. So this process is going to give us an intermediate, which is now our OH. Let me just keep the color coding. OH. This would be a positively charged intermediate, because what we've done here is attack with a neutral nitrogen, or neutral oxygen, excuse me. And then we've got our sort of imine looking structure over here. This carbon-nitrogen double bond is what we have remaining. So if we're going to move forward in this, if you look at what generally has to happen, remember we're trying to get to a carboxylic acid, which is going to have our carbon-oxygen bond. This is kind of set up to be that kind of the acidic OH. And then here we have this carbon-nitrogen double bond. We need to replace this center with another oxygen. So if we're going to carry this mechanism forward, next thing we have to do is similar to did with the hydrolysis reactions we've seen before. We need to get rid of a proton from this acidic center, otherwise the reaction might just proceed back to where we started, and we have to add another proton to this center in order to help it to leave. So we're going to end up with proton transfer to change out our centers. So if you think about it, we're going to have other molecules of water in the system. You could draw this as picking up one proton from that center to give us our R double bond nitrogen, hydrogen, and now OH. We have the catalyst. Now we've passed the proton back to the solvent here to give us this, which then can transfer that proton back to our oxygen center. So now what we've done is set ourselves up for another round of attack, because what we've done is protonate this nitrogen. Once again, we've made the center carbon more electrophilic by polarizing that nitrogen center, and that allows another molecule of water to tack into that center. Let me draw that more direct, like that. So Now what we have is a nitrogen. We have our two hydrogens attached to it. It's now neutral. We have the first water we added, and now the second one, like this. So you can see the pattern that we're sort of carrying through here. We've now gone to a tetrahedral intermediate. Once again, just to highlight, we have 1, 2, 3 carbon heteroatom bonds. That's really the same thing we have here. We're just shuffling around on changing pi bonds over for sigma bonds, but same oxidation state. Now, obviously, this is not quite as stable. This is probably much higher in energy than having our pi bonds, but under acidic conditions, it allows us to access this one. What we're doing as we move this reaction forward is really being driven, like we talked about with acetal chemistry. It's really Le Chatelier. Having lots of water and the acid catalyst in time will help us to access this molecule. So it's not really thermodynamically driven. This is driven by just main mass transfer and amount of material. So after we've made this one, it's time to collapse back. Like we still want to get rid of this final nitrogen. We want to regenerate a carbon-oxygen double bond as we go through this kind of process. So let me just add a page in between, and excuse me. I'm going to grab this intermediate here. And copy and paste. All right. So continuing on from this intermediate, what we need to do, once again, is migrate a proton from where it's positive, this oxygen, to the leaving group we're trying to use over to the nitrogen. So we're going to do that again using, let's say, another molecule of water. We'll color code it differently just for bookkeeping. So what that's going to do is make that center neutral, and gives us the now neutralized intermediate. We have our OH, second OH, and the remaining NH with, sorry, keeping the color code that we did, with our positive charge latent here. Means we can transfer the proton from that acidic oxygen over to the nitrogen. That gets that nitrogen now ready for loss, right? We're going to take a positive charge over here, which makes it into a better leaving group. And we have our OH and OH like this. So to finish off this mechanism, one of the two oxygens is going to act as a nucleophile. We can take the lone pair and reform this carbon-oxygen double bond, sacrificing the ammonia as our leaving group in this way. Either of the two oxygens, you can choose. Both of those are equivalent, so it doesn't really matter which one you choose to use. But what that gets you to is something that looks pretty close to your carboxylic acid. Right now you're down to here. Actually, if I keep my color coding from before, we've got one OH like this, and the other one is our OH plus from before, and we have now kicked out NH3, ammonia. Last step is to just pick up this proton, and that's going to give us our final molecule, our now fully hydrolyzed carboxylic acid plus NH4 plus as our final sort of center. Again, it's this last deprotonation here. We're going from what might be a charge carrier like the protonated water as our acid catalyst. Because we're generating this one molecule of ammonia, that's a very good base. Generally, that'll help to pull the equilibrium forward to our product over here as well. So those steps are just detailed over here in our full chem draw. So once again, activation, we're under acidic conditions, so we don't have a strong nucleophile, we have just water around. We're going to activate the electrophile to make an activated electrophile, kind of like our aminium. That's going to be attacked by neutral water to make our positively charged intermediate. Proton transfer, where we're losing a proton from here and gaining it on this nitrogen, gets us ready for the next attack. We're going to go once more to make a tetrahedral intermediate where we have 2 oxygens and 1 nitrogen on the same center. Once again, another proton transfer step where we're losing 1 proton here, gaining on this nitrogen. Once again, moving forward where we're trying to get rid of this nitrogen, keeping 2 oxygens. And then collapsing that, reforming a carbon-oxygen pi bond that's much more stable, giving us our ammonia. And our last step is just a final proton transfer to get to our carboxylic acid. So now we're going to do the same thing, but under basic conditions. Now, the base condition proceeds through an amide intermediate, not the same sort of tetrahedral intermediate. The second part of the mechanism will show up again in the next chapter. We're going to talk about this as we go from amides to carboxylic acids. There are many different variations of this mechanism. We'll show you a couple different points because there's some interesting energetics that are possible here. I'm going to show you a version of it. You may see other ones online. Really, I'm not a stickler for which one you choose to use. I'm going to show you the one that sort of makes the most sense to me, but you'll see that the intermediates we generate are different than what we've seen with the acidic condition, and please feel free to follow whatever correct mechanism you may prefer. So the main difference is here. When we're under basic conditions, you have a good nucleophile. Remember, under the acidic conditions, all we had was water as our nucleophile. So because we have a strong anionic nucleophile, we're not going to be activating the electrophile to start off with. This is very similar to what we saw with the base catalyzed acetal formations as well too. So we don't lead off with a proton transfer, and that's also again following that we got basic conditions, so protonating this is a no-no. We're not going to be doing a proton transfer to make cationic intermediates under basic conditions. We're going to be primarily anionic intermediates as we move through. So the nucleophilic attack is going to be first to generate this intermediate. Now you can already see that there is an interesting problem we're sort of starting into here. What we just did is punch up and create a nitrogen minus. So this is already a relatively high energy intermediate, right? We've kicked a negative charge out of this nitrogen. Yes, we broke this carbon nitrogen double bond. We've been pushing in with this oxygen minus species, but we're kind of going uphill in energy here. What this will generally do is reform another molecule of base because we are under aqueous conditions. So we're just going to deprotonate another molecule of water relatively quickly to give you your neutral intermediate. We now have your NH and your OH type system. Now, in here, in order to move forward here, and again, just follow me through with what's happening, and we can sort of discuss the different potential energetics here. But to move forward, we now have hydroxide. Remember, the overall target we're trying to do here is completely remove this carbon-nitrogen double bond. We're going to be adding in another molecule of hydroxide in order to do that. Now, from this particular compound, if you recognize this, this looks a little bit weird. We've got this carbon-nitrogen double bond, and we have a carbon-oxygen single bond. You should recognize this is actually a tautomer of our normal amide compound. So what we can do is remove a proton, other way around. We're going to remove a proton from this oxygen. Here, And by doing that, this is similar to the base catalyzed mechanism for keto-enol tautomerism that we saw in the last couple of classes. So now what we've got is our negatively charged center over here. That can very easily migrate and pick up, let's say, a proton from another center, or you could look at it as, well, actually let's look at this first of all as an equilibrium, right? If I was to draw this as a resonance isomer, that negative charge can delocalize out onto that nitrogen. So we can draw this as a double bond to our oxygen and a negative charge over here onto nitrogen. So what I'm trying to emphasize, if you remember in previous lectures, if I had, let's say, a ketone like this, under basic conditions, that would be deprotonated to my carbon-centered anion, which then is under resonance to our enolate, right? Where we're putting the negative charge onto, let's say, the more electronegative center, but we have this ability to delocalize this negative charge amongst sort of a 3-atom system. That is a precursor to the keto-enol tautomerism, where we could potentially protonate this negative center to get to our enol. Here, protonating this nitrogen gets us back to actually an amide type structure. So let's finish that part off. Again, this is just a reminder that what we're doing here, even though we've got these oxygens and nitrogens, it's very similar to what we've been showing for the keto-enol tautomerism at this step. So first, by deprotonation on the oxygen, we get a resonance stabilized anion, and then that can be now protonated from, let's say, a molecule of water to get you to your amide bond form. So this is a key structure that we get under base catalyzed hydrolysis. And in fact, this molecule here, this primary amide, is typically where we're going to stop. Under mild base conditions, the hydrolysis of our nitrile will typically get only as far as a molecule like this. So the base catalyzed addition gets us through to something which can get to this tautomerism route and then actually stop as this amide. So this is actually a quite stable component. And just on top of it too, if you compare this back to the acidic mechanism that we showed you through here, typically base catalyzed or base hydrolysis of amides requires much higher temperature and much longer times. There's two reasons for that. First of all, this nucleophilic addition of the hydroxide is quite difficult. Being able to activate it with a proton like we do in the acid catalyzed one is actually preferable. And then second, we get stuck at a very stable intermediate. Stopping at this amide is actually very common. Pushing this through to the final hydrolysis is actually kind of difficult. So again, if we're going to continue this forward and do the entire hydrolysis, let's start here again. Oh, excuse me. And I'm just going to copy this, and let's jump over to our next structure. So if we're going to continue this hydrolysis, we are still under basic conditions. It's not very favorable. This is very difficult. But if we want to completely remove excuse me. If we want to completely remove this nitrogen, we need to replace it with an oxygen. And we're going to use something similar to what we showed in the first mechanism. We're going to do a nucleophilic attack onto this carbonyl. This allows us to park the charge out on the oxygen temporarily. This at least gets us the new oxygen into system. So we now have that. We have our NHH like this, and we've added in that one more oxygen, that's hydroxyl. So this is the tetrahedral intermediate we're going to form now under basic conditions, and notice that it is negatively charged through here. Now, to get forward from this one, this is a relatively destabilized system, and if you just look at tactically what we need to do here, this is kind of primed to help potentially eject the nitrogen. If you've seen in other cases, if I was to bring this down here, what I'm going to be doing is breaking one of these sigma bonds and helping to remove it from the center. So if I were to just bring this one down and eject this hydroxide, we'd be going back to the starting material we show here. So that's a common state that we do from these tetrahedral intermediates, is this collapse will be coupled to some sort of an elimination. So this would just be going back to our starting material. What we really want to do is bring this back and then kick out that nitrogen. The problem is, remember, just like we've shown you before, if I was to break this bond on its own, I'm losing nitrogen minus. That's not a good leaving group. So there's a move we can do here, and this is kind of similar to what we've seen with the imine formation under basic conditions. It's possible potentially to, let's say, transfer a proton from water temporarily. Now, not very favorable, right? Like, this is not a very basic nitrogen. We're making hydroxide as we go through this, but if you look at the molecule we form, we at least make a Zwitter ion, right? So it's, yes, it's oxygen minus, but what we now have up here is NH3 plus, which at least overall, this is a neutral molecule overall. It's a Zwitter ion where we have both positive and negative charge. Not very high concentration. This is a relatively high energy intermediate, but at least allows us to activate it and form a good leaving group on this nitrogen center. So last step, we bring in this oxygen and we now eject that NH3 plus. That gets us to our final carboxylic acid like this, and NH3. So at least as we move through this point, we get a molecule which allows us to eject this nitrogen as a neutral species, albeit we do have to go through this relatively high energy zwitterionic type structure, still a little bit lower in energy than the anion we form over here. This attack in particular is very difficult to do. You're taking a not very activated center, a relatively good nucleophile, but this is an equilibrium that is very, very, very far in favor of the starting material, you could say. So the overall impact of this is when you do the hydrolysis under basic conditions, most important, number one, we do not need to activate this nitrile to begin with. We don't have any protons available. The direct attack is possible to create this high energy iminium type species that then rapidly picks up a proton to make this compound. That compound is related by a tautomerism over to the amide structure. And again, because this first attack is very unfavored, this is a very slow process to get this far. And typically the amide is isolated, this primary amide, it can be stop the reaction here, and we'll talk about this a little bit more in further lectures. So even if you do get to this one, after really, really pushing on it with strong base and high temperature, remember just the quick reminder that the two structures we're seeing here are just simple tautomers of each other. That's an analogy to the keto-enol tautomerism we showed you in the previous lectures. Finishing this off, once again, we still have to get rid of this nitrogen center. In order to do that, we're going to have to make it into a better leaving group by first protonating it. So after this nucleophilic attack, to make that same kind of similar tetrahedral intermediate, notice under basic conditions it's negatively charged. We're going to protonate this nitrogen to make it into a better leaving group, and then we're going to do our nucleophilic attack to give us our final compound. One thing that we often note as well, because we are under very basic conditions, you typically will be deprotonating that carboxylic acid so it'll exist as the carboxylate until actual workup. Again, the main focus here is that the protonation happening ahead of time for the nitrogen addition is generally what we would favor. So with that, thanks very much. Again, apologies for missing out on the lecture, guys, and I will pick up with you guys on Wednesday.